Okay, so let's look at this practice test. It's a review for the test over indicators 9, 10, 11, and 12. So I'm going to zoom in on this a little bit, see if I can. There we go. So let's look at this first one. Solve the equation given the domain for the range. So we want to know the range of this. And they give us the domain and they give us the rule for generating the y values. And they want to know, what is the range? So they give 4 sets of ordered pairs. Now, we could do this the old fashioned way and just um, make our table like we did, right? And write our rule, y equals 2x minus 1. And we could generate all those y's and we could make our ordered pairs. Now, we've done several problems like this. So I'm not going to go ahead and work this one out um, like that. Instead, we might take a shortcut and just try to eliminate some of these. There's nothing wrong with doing it the long way. It might be the most surefire way to do it. Put your X's here. And again, we've done several of these, so I'm not going to go ahead and do it the whole thing. But we would have to go ahead and generate Y's for each of those X's. Okay? And then say, okay, which of those agrees? But let's take a shortcut. We can look at these and eliminate some of them. And one thing I notice is this one, the A has a 5 for X in one of these ordered pairs. There is no 5 there, right? So we know right off that A cannot be it. Okay? Whoops. So we eliminate A. And then since we don't have to worry about A, we can say, okay, for the point -3, or for the x value of -3, we have 2 possibilities among our answers. B says it should be, B and D both say y should be -7. C says something different. So let's go ahead and find out that one. Okay, so we have our table over here. It's pretty handy. Let's go ahead and calculate that. 2 times x minus 1, and we're going to try -3. So 2 times -3 is -6, minus 1 is -7. Okay, so C said it was -6, so C is not right. We've eliminated that. Now we just have a couple of them. Where are those different? Okay, if we look at them, they're the same until you get to here. And so all we need to do now is see which one of those is correct for the value x equals 1. So we've got that on our table. We'll calculate that one. 2 times 1, we put in a 1 for x, right? Minus 1. And that comes out to, I'll go ahead and fill in the -7 here. That 2 minus 1 is 1, right? So that says this one is it. Okay. We didn't check the rest of them. We're strategically saying, well, if one of these answers is correct, it has to be B, okay, because of the ones that we did check. We eliminated D just then because it's wrong for that point. So that's one way to do it. And we say the answer B. You could also calculate all the Y's. That we've done a lot of them that way, so I thought, we'll do this one a different way. Okay, which relation is a function? We're just looking for ones that don't have any repeats in the x's, right? If it has a repeated x, that would be an x value that has 2 different y's that go with it. And we know that's not a function. So the very first one, I don't see any repeated x's there. That looks good to me. So I'm going to say A. We might as well look at the rest of them. So B has a repeated x there. Two different y values go with 3. So that's not it. C also has a repeat, has two different y values, a y value of 10 and -2. Both go with 5. That's not it. And then D has the repeated 6. Two different y values paired with 6. Okay, not a function. So it's A. Okay, here's the next one. We want to find f of 3. Given f of x equals 5x plus 2, you just plug it in very carefully. F of 3 is 5 times x. We write the parentheses for x plus 2. And we put in a 3 for x. So we get 15 plus 2. 17 is what I get. Pretty sure that's correct. So that would be D. Okay. Let's keep moving on. Which relation is a function? I like this problem. It says, I like it because it fooled me for a second. It's a function if it passes the vertical line test. So it's a function if you cannot draw a vertical line that crosses it twice. So the first one, we think, well, every vertical line is only going to cross that once. Looks like it passes. B clearly fails, right? We draw a vertical line, we quickly find vertical lines that cross it twice. Not B. C, you think, okay, vertical lines look like they only cross it once. Looks pretty good. It looks like there's two correct answers. I mean, I know A is correct, so there's only supposed to be one correct answer. But look at these vertical parts of the graph itself. Okay, this graph for C, parts of it are vertical. So what do you make of that? See, you have these stair-step deals where it's actually vertical on all of those. Well, of course, if you look at one of those and you draw your line right there, your vertical line is actually superimposed on that line. Okay, so definitely your vertical line, if it's drawn on any of those, it's superimposed right on it. It does cross the graph in more than one point. If we draw that like that, this entire stretch, they are superimposed on each other. That's a lot of points of intersection. Okay, so the graph does intersect our vertical line, not in just a couple points, but in lots of points. This entire, see where I'm coloring it in thick there? That entire stretch of points intersect with the vertical line. They are in common with the vertical line. It fails, okay? It's easier to see when it just crosses it a couple times, like on B, when we draw our vertical line, it crosses it twice. Oh, yeah, it fails. But on C, it actually intersects the graph on many, many, many points. Definitely fails. Okay. What is the domain of the following function? Oh, did I write the answer in for that one? Let's be complete here. We said it was A. Put the answer in. Okay. Number 5. What is the domain of the following function? Don't get fancy on this. Don't miss this. Do not try to write a compound inequality. -1 less than or equal to x less than or equal to 11. Do not do that. Okay, that would specify an entire big set of points, right? If you write a compound inequality like that, you're saying, for example, 0. 0 would fit that compound inequality. 0 is in between -1 and 11, but 0 is definitely not in our domain. Okay, those are the only numbers in our domain. So when you're given a list of ordered pairs, you just write down the x's, the x values of each ordered pair, and that's your domain. Domain is simply the set of all possible x values of a function or any relation. And when they give you the list of ordered pairs that are in that relation or function, that's it. Those are the x's. That's it. Okay, just list them. Okay. What is the range of the following function? So for this one, number 6, we just list the y values, right? That's all. Don't write it a compound inequality or anything like that. That would imply far more values than are actually in that range. This list of ordered pairs is the function. So what are all the y values? Well, there they are for us. We just write them down, the y values for each of those ordered pairs. -2, -4, 6, -8. And sometimes this seems too easy and people think they need to do something else, but no, that's it. Just don't write down any repeats because you only need to write the number once. Okay. Number 7, determine if the following relation is a function. If it is not, give the reason why it's not. So all you're looking for is, are there any repeated x values? So this first one does not have any repeats, so it is a function. We'll just say yes. Okay, or you can say, yes, it is a function, or you can just write the word function, however you want to do it. And then the next one, okay, lots of repeats, right? 2 is paired with 3 different things, so that is not a function. Not a function. And the reason, you could just say 2 repeats. That's good enough. Okay? Okay. If g of x equals 3x times x minus 4, find g of 2. Okay, so let's do that. G of -2, sorry. All we do is g of -2 equals, we just plug in -2 for each x, right? I write parentheses in place of the x. Be a little careful here. We're going to put parentheses inside parentheses. Not so tricky. Okay? We have these parentheses that I have the arrow on. They're part of the function, and then the ones I wrote are here. Okay? So we just plug in our x, which -2, we plug in for x. So 3 times -2 gives us -6. That's outside the parentheses. Inside the parentheses, we just evaluate this. -2 minus 4, that is -6. I didn't have to write those parentheses so large, but that's okay. So now we have -6 times, let me shrink that down and make it look better. So inside the parentheses, it comes out to -6. So -6 times -6 is, drum roll please, 36. So that's it. Okay. Now we have one of these, find the range of the following relation for the domain. We've done a lot of these problems. I think to save time, I'm not going to work this all the way out. It doesn't say to write it as a set of ordered pairs, but you could. But I will show you how to do it. So our x values, we have 4 of them, -8, -4, 0, and 4. And I should have zoomed this a little bit bigger. Let's do this again. So we have more room. Okay. So -8, -4, 0, and 4 are the x values, and we have a rule. Y equals 10 minus 2x. This is the easier kind of problem because they give us the rule. Okay, in the other kind, You might have to find the rule yourself if it was an equation that was not solved for y. This one is solved for y already, and so we have our rule. We don't have to solve it for y. So we have y, and then we could write our column of ordered pairs. So we would calculate each of these, right? So we could write our rule down. Here, our template, 10 minus 2 times x, and do that for each of them. And plug the number in, -8. -4, 0, and 4. Calculate each of those y's. Well, maybe we might as well do it. Hopefully I won't make a mistake because I'm going to be doing this quickly. 10 minus 2x. Okay, I think I'm doing it right so far. So that becomes 10 plus 16 there. 2 times 8, -16. So I think that's 26. So, and then we have 10. I think that comes out to plus 8. That's 18. And then 10 minus 8 is 2. So that's all of our y's, and -8, 26 is that ordered pair, and then -4, 18, and then 0, 0, 10, and then 4, 2. Okay, hopefully I didn't make any mistakes there. Okay, so let's look at 11 and 12. Find the best graph to match each scenario. And the first scenario, we'll do this one fairly quickly. It's a pretty good problem, but if you read it, you'll see the first scenario has describes the train ride at the zoo. Molly and her mother ride the train each time they go to the zoo. Molly knows that the train slows down twice so that the passengers can view the animals. Her favorite part of the ride, though, is when the train moves very quickly before it slows down to approach the station and come to a stop. Okay. So then the second one says, Philip is flying to Texas for a business meeting. When his flight leaves, the airplane increases its speed a great deal until it reaches about 550 miles per hour. After 20 minutes, the plane levels off for the last 45 minutes at 500 miles per hour. As the airplane nears the airport in Fort Worth, Texas, it decreases its speed until it lands and reaches 0 miles per hour. So, well, right off we see the first scenario, this one we read up here, talks about it slowing down. Okay, it slows down twice. So, well, that looks like that's going to be B, right? So we already think that's probably B. The other one talks about the airplane increasing its speed a great deal, and then it slows down some. It even tells us 550 miles per hour and it slows down to about 500. So if we look at this top graph, that looks about right, correct? It speeds up to this speed here, and then it slows down and goes about this speed here, which is less on speed. So yeah, it looks like that's probably that one. So yes, we will say 11 is B, the train ride. That's the one where the speed goes up and down. And 12 is A, the plane. Okay, it goes faster, then slows down somewhat, and then slows to a stop at the end. Okay, so now we have some from indicators 9 and 10. So this is indicator 10. Sketch the graph for the given situation. Sydney went on a jog, and before we even read about Sydney's jog, we probably should look, what kind of a graph is this? Because if we know what kind of graph it is, it guides our thinking of what we're going to be looking for, what we're going to have to do. This is a distance-time graph, distance versus time, we might say. Okay, so let's read it. Sydney went for a jog for 15 minutes. She stopped to stretch and drink water for 10 minutes before walking for 10 minutes. Okay. So she jogged for 15 minutes. So we just know we're going to have her jogging until this far. Our marked 15-minute mark on their time. She's jogging, and it's a distance time graph. So we're going to show her distance increasing over time. Starting at 0 and increasing, she's jogging. So we'll stop and think, okay, how far might she jog in 15 minutes? Maybe just a mile. That would be really slow jogging, maybe a mile and a half, couple miles. Don't worry about it. Say, let's just put her right there. And she was jogging to get there, so her distance increased. And so we have that. Then she stopped, so her distance is not increasing. It's going to be 10 minutes. So she's at 15 minutes, so we take her to 25 minutes, about right there. And she doesn't move at all during that time. So her distance stays the same. Then she walks for 10 minutes. So that's going to take her to the 35-minute mark. So you just look down at your x-axis and see how far she's going to end up. Where on the x-axis will she end up? 35 minutes. Okay, that's 10 more minutes past where she was. And she's walking. We just need to show a smaller slope, because now she's walking. She's not going to go as fast as she was going. So we do something like that. And that's it. Okay, problem is done. Okay. Look at the next one. FFA went on a trip by driving 50 miles per hour for 30 minutes, then stopped to eat for 20 minutes. Then they continued to drive 60 miles per hour for 1 hour before arriving at their destination. So while I'm reading this, I'm hoping this is a speed time graph. I didn't look, but if it's a speed time graph, it's going to be pretty easy. A steady 50 miles per hour for 30 minutes, I can do that. And then they stopped, so then their speed's going to go to 0. It'll be real blocky, 50 mile an hour, then 0. And then they drive a 60 mile per hour. Whoops, their speed's going to go up real quick to 60. I can do that. I hope this is a speed time graph. And I have that off the screen, so I can't even see it. But, whoa, this is not a speed time graph. Rats. This is a distance time graph. So my little thinking did not help. I should have looked at the graph before I started and said, this is distance time, but that's okay. We'll figure it out. So it's a little bit more work, right? It tells us she was going 50 miles per hour for 30 minutes, and we have to figure out how far she went during that time, which isn't too bad. I suggest probably the best way is just do this in your head, 50 miles per hour. Okay, and she went for half an hour. So she went 25 miles. And you could do it on paper like this, 50 miles per hour times half an hour. Don't write 30 because it's 30 minutes, right? And our units of speed are miles per hour. So our distance needs to be hour. So 50 times a half. And if you want to notice, I think it's pretty cool, you could cancel hours, and 50 times a half is 25. We canceled the hours, the only units left is miles, 25 miles. So that's how far she went. You could just do it in your head though. So let's mark off the 25. Whoops, that's 30 miles. Um, 25 miles is actually, oh no, wait. I was looking in the wrong. Yeah, sorry about that. We need to mark off miles, not minutes. So she went 25 miles. So I was on the wrong axis. Sorry about the confusion. So 30 would be about here. I'm just going to write that down just for fun. 25 is about here. So that's how far she went, 25 miles, and it took 30 minutes to get there. So the 30 minutes is the time. We could write 30 like that. So 30 minutes, she went 25 miles, so it's right there. Okay? And she went at a steady speed to get there, so it's a steady slope. Okay? Um, So then they stop to eat for 20 minutes. So this one's making us work a little bit on this axis. That's 30 minutes. So we want to go to 50 minutes. That's 20 minutes later, right? So just, you don't have to write the 50 down, but I did. I'm going to write that a little bit more accurately. Right in between 40 and 60, hopefully. That's better. There's the 50 minutes. That's how, at the 50-minute mark is when they started back up. So they stopped to eat lunch for 20 minutes. From 30 minutes to 50 minutes, they did not go. So their distance did not increase. It's just a flat line. Try to make that more accurate as well. And then what happened? They continued to drive 60 miles per hour for 1 hour. This time they drove for 1 hour, so 60 mile per hour for 1 hour. That's 60 miles. So we've got them going 60 more miles. So from 25 to 85, and I marked 90 here to help me mark 85. So that's 90. So 85 is right there. And it took them 1 hour to get there. So that's 50 minutes is where they are at the end of their rest. And so it's going to be 60 more minutes, 110 minutes, which is right here. 110. Okay. And so at 110 minutes, they've 85, which we marked a while ago on the distance on the y-axis. So it's about right there. Okay. That's 110 and 85. Okay. So we just connect that, and that's it. Okay. I think we just have a couple more. So these last two are like the indicator 9. We're given a graph and we're asked to analyze it, say some things about it. So here we go. The graph below shows Jamie's heart rate during different parts of her 20-minute treadmill workout. So there it is. So we answer the questions. Which segment shows no change in heart rate? Okay, so which is that? We want the one where the heart rate does not go up or down. Remember, this heart rate is our y-axis. So that's where the heart rate is flat. So that's right here, which is D. Okay, and then they say which segment shows where Jamie's heart rate increased the most? That is just the steepest slope. Okay, that's where it increased the most. So we look at that, and that's A, right? That's where it's steepest, so that's A. Okay. Ashley's bike ride home. I think this would be better, say, Ashley's round trip. I'm going to change this because she ends up the same place she started. So when you say Ashley's bike ride home, that sounds like she started somewhere and ended at home and maybe came from her grandmother's house or something. But we know from looking at this graph, the distance from wherever she starts, her distance is 0, and it ends up at 0. She's back where she started from. So that's why I would rather say Ashley's round trip. So let's change it to that. We don't really care where she started and ended, but we know it's the same place because the distance is 0 at the beginning and at the end. So Ashley's, let's just say her bike round trip. Okay, so what's happening in segment A? There's no distances or times. There's no actual numbers here. So this is a little easier, but in a way a little harder. If there was times, we would say, okay, she rode for 30 minutes. And during that 30 minutes, she rode a certain distance, 5 miles or something. But it doesn't have anything. So we'll just say she rode at it. We can say she rode at a steady rate. We can say that much. How do we know she was going at a steady rate? We know that because the slope is constant, like most of our graphs are that we do in here for these type of problems. The slope doesn't change. That means the rate doesn't change. Slope is rate on a distance time graph. Okay? So what's happening in segment C? Well, segment C is where the graph is flat. Distance is not increasing. However far she was from home at this point in time, she's the same distance at this point in time, right? She's this far, whatever that is. So she's not going anywhere. So we could just say resting or stop to rest or something like that. Probably better to say resting because this is over a period of time. She's not going anywhere. What is happening at segment D? And she's riding back to where she started, right? Her distance now is getting less. She's getting closer and closer over this segment D to wherever she started from. So we'll just say going back to her starting point. And that's enough to write for that one. Riding back to starting point. Okay, so what does the y-intercept represent? That's a good question. And for any of these graphs, the y-intercept is just the point where you are it's the starting point, right? Because the y-intercept, that's where the graph crosses the y-axis. And what's important about that, or one of the things that's important about the y-axis is that's where the time is 0, right? The y-axis, right? Where the graph crosses the y-axis, right there, the time is 0. So that's the distance at time 0 is the starting point. Okay, so we'll just say starting point. Okay, at time 0, how far were they? In this case, the distance is also 0. Okay, so I think that's all the problems. Hope that helped. Just a few from some of the indicators, but that is something of a review. So hope the test goes well, and I will see you later.